Up. You're never going to understand it anyway. Okay, Jeff says time to start. All right, so as I was casually saying, we've only got 4 more lectures, and I want to spend at least 2 lectures on rheometry, the measuring of rheological properties. So that's what we'll do next week. So I'm just going to talk about advanced polymer constitutive equations this week. So that's today. And then tomorrow at 10, which is the rescheduled lecture, and then Friday at 3. So let me try to, I guess I'm going to have to skip some of the derivations and just indicate to you what the logic is on some of these calculations. So going back to the beginning on advanced constitutive modeling, remember that we're looking for constitutive equations, which are these tensor equations here. Tensor stress. Okay, we'll see if I can get this going here.
Can I ask a question real quick?
Sure.
In the homework, they switched from the g of t minus t prime to the g of s. And then they switched the limits of integration as well in the book.
Right.
Since you're switching from negative infinity to t to 0 to infinity, and that pretty much flips which order they're in,
Correct.
shouldn't there be like a minus sign that comes out of that?
It's because you're also changing dt prime.
Okay.
So it's the integral from minus infinity to t, and then remember that s is equal to t minus t prime. So ds is minus dt prime.
Okay.
T minus t prime. And so there's, when you switch to s, this becomes infinity. This becomes 0. There was a minus sign out front, and then you switch the order. Is that right? Tau equals, so this minus sign goes with that, so you get ds. And then it's positive out front, but then when you switch the order of the integration, you get the negative sign back.
Okay.
Okay? Does that sound right? Okay, so we're talking about advanced constitutive modeling, models that work better than the generalized linear viscoelastic model, but that will also predict time dependence and hopefully other types of dependencies. So what we've talked about so far is that the path we're taking is to improve the strain measure. And so I went through an exercise to turn this strain rate tensor into this strain tensor through an integration by parts. And this front factor changed as well. This was g of t minus t prime, and this is m, which is partial g with respect to t prime. So this function is something that we can get from experimental data. So this is a usable version of the generalized linear viscoelastic model. But the important thing for us is that it changed our focus to strain measures. Then I talked about that strain measure, and I pointed out that in, say, for example, the simple rotation of a block, it predicts that there's an angular dependence of the stress in rotating a block, which is not true. And we got to that by doing the formal calculation of the strain measure, which has the angle in it. And so we get a stress proportion that is a function of the rotation, which is a problem. So I identified that problem as related to the strain measure. So what we've been working on is new strain measures. The technique that I proposed to you for finding new strain measures was to keep track of the distance between 2 close by particles when it undergoes some sort of a deformation. And I just used the chain rule to develop the deformation gradient tensor F. So the deformation gradient tensor, just to cut through any confusion, is a tensor that relates the change in the x position of particles y position, z position of particles. So the prime is the old, this f is telling us we're going from t to t prime. So x prime, y prime, z prime is the new location of the particle. X, y, z is the old location. And this is relating, this is just organizing it. We haven't said much about it, but somehow it should be related to the change in shape when we go from one state to another. Now, just mathematically, we can find the inverse of this tensor, again, employing the chain rule. And that tensor is this one, the inverse deformation gradient tensor. So they both, this one measures deformation from t prime to t. And we did a little practice on that, and we calculated it for shear flow. And I also showed that we have a table for some common deformations in the textbook. And here was the result that we got for shear flow, and there's the result for F inverse for shear flow. And then going back to the rotation, there's the rotation tensor for this particular strain measure, and here's the inverse of the rotation, so rotation in the opposite direction, which you can get from this to this by just changing the sign of psi. Okay, so I've essentially gone over these first two columns in this table, and we could do it for uniaxial elongational deformation, or in fact any deformation. It just gets a little bit trickier. Now, all we've done is define two new strain tensors. We don't really know how good they are. And I identified that the problem, going back a few slides, the problem with our old strain measure was that it used u, the deformation vector u, which is just the difference, going back to this sketch. Where's my sketch? This sketch. Just the difference. So it's related to the vector that connects the position vectors at the two times. And this is going to have, this F is going to have the same problem that gamma had, because it is going to take into account rotation. So our next step is to get rid of the rotation effect that is implicit even in these new strain measures. And this is where we pull out some results from linear algebra or vector calculus. And we're going to look for a way to separate rotation and stretch for these type of strain tensors. Okay, so as I just said, all of these strain measures, del u, our old gamma, which appears in the generalized linear viscoelastic model, and the two new ones, they both depend on deformation and orientation. The trick to get rid of them is a technique called polar decomposition. So as I said, because we're not going to be able to spend a ton of time on these things, I'll have to be just descriptive in how this works. This is a polar decomposition theorem says that any tensor for which an inverse exists has two unique decompositions. So I can write any tensor for which an inverse exists, for example, tensor A, as the product of two tensors given by these formulas down here. Okay, so these are very particular tensors. U is A transpose A square root. R is this combination, A dot A transpose A square root, 1 over. And then V is another portion of a decomposition, A transpose, so you see they're in different order. And R again, the same R. So this is a result from mathematics, and the advantage to us is that it separates out a rotation. So this tensor R is a rotation, and this tensor U has all the stretch in it. Or, for example, this tensor V has all the stretch in it, and this tensor R is the same rotation tensor. Now, I did an example in the book so that if this is of interest to you and you want to really see how it works, you can do the calculation. You can pick a tensor A, and this tensor A can act on a vector u. And if I act this tensor A on this vector u, the vector u becomes a vector v. So that's just normal. A dot u is v. And so A had the effect on u of rotating it and stretching it. Now going back to the decomposition, if I apply A dot u, that's like going R capital U small u. So I can rotate it. That's what the u does. I rotate and stretch, and then the rotation of R. Or I can do this decomposition. So if I applied the u here, I apply R to it first and then v. And so that would be like rotating it. I don't have that sketched here, but that would be like rotating it by the same amount that R rotates it, and then stretching it and rotating it to the final answer. Okay, so let me just give you something to see with all those words. Again, I'm doing A dot u equals v, and that's the same as R dot cap u dot u, which is v, or v dot cap r dot u equals v. So these are both equal to A, so I've done nothing interesting. But the effect is that first u acts on little u, then R acts on the result, or first R acts on little u, and then v acts on the result. And at the end of the day, you have to get this final v every time. So one thing you'll notice is that we've only partially isolated the effect of rotation. You see in this example that when I applied u, it rotated and stretched. But we have taken all the stretch out of the R part. And so the other trick is to now go back to our original idea that we're using these as strain measures. And we weren't very specific about what we needed to follow in doing a strain calculation. And now we can choose to be specific. We're going to choose to focus on the eigenvectors of these two stretch tensors. And by concentrating on the eigenvectors of these stretch tensors, we're going to completely eliminate rotation. So let me explain what that is. From your linear algebra studies, you've heard of eigenvectors and eigenvalues before. So for instance, you've studied a matrix has certain eigenvectors that when you apply that matrix to the vector, you get the same vector back, just multiplied by a constant. In the context of a strain tensor, if this is a strain tensor, and I apply it to a vector, this equation, this eigenvector equation, tells me that it just stretches that vector. And that's what we were looking for. Okay? So any vector that we're looking, so this u is a strain measure. If I apply u to an arbitrary vector, v or something, or a, then I can expect that the result will be some new vector b. It won't be parallel to a. It's going to stretch it, and it's going to rotate it. But if I apply u to its own eigenvector, that's a very specific and particular vector, which will give me that same vector back stretched. So here there's both stretch and rotation, and here there's stretch only. And that's exactly what we hope to do. Okay? So u is a tensor that has all of the same stretch properties of the original tensor. And if we use the eigenvectors as our measure of deformation, we have in u completely isolated stretch. The key is that both A and U have the same amount of stretch. So in this sketch, I show this as well. If I act U on its eigenvector psi k, okay, here's my original psi. I act U on it, it only stretches it. So psi becomes lambda psi. And then because I want, let's say, to do the entire transformation of the A tensor, it would then transform it into its final result. Let's say B. The missing piece is the rotation tensor. Now, we have two of these stretch tensors going back here to the polar decomposition. We could decompose it two different ways. One is the left stretch tensor, one is the right. And it turns out that their eigenvalues are related to each other, so they don't do anything different, as they really shouldn't, because they're both characteristic of the same deformation. The only difference between using the eigenvectors of V or the V and its eigenvectors or U and its eigenvectors is whether you rotate first or stretch first. So in the case of V, you start with the eigenvectors of V, you rotate first, and then you stretch, and you get to the final result. The eigenvectors of V and U are only related by the rotation tensor. They have the same eigenvalues. So I'm not showing you all of that. I'm just talking you through it. The main concept to take is that we have a deformation which will be it's going to be our F and F inverse. Those are our deformation tensors. They follow the deformation from an initial to a final state or from a final to initial state. One goes forward, the other goes back. They both have a rotation and stretch. And if you understood what I just said, you can see how I can take rotation out. If you didn't understand what I just said, you can at least understand that that's what we've done. We've taken out the rotation and just kept the stretch. And that's going to fix this problem of generating stress by just rotating a cube of fluid. All right, so going back to our deformation tensors, we have F and F inverse. And we can form these stretch tensors, V and U. Now going back to the definitions of V and U, they have a square root in them. Since we don't really have to do exactly what this says, we're going to just consider the square of U and the square of V so that we don't have to take square roots. So if I formulate the square of U and the square of V for our two deformation tensors, V and F inverse, I get F transpose for V or F transpose F for U. If I do the same for F inverse, I get F inverse transpose, F inverse transpose, and F inverse transpose dot F. If I take the transpose F, because really these were kind of arbitrary deformations in the first place, we can create other combinations. So if you look at this table of all these new strain measures I've created, there's really only two that are distinct. FF transpose and F inverse transpose F inverse. And these are called the Cauchy tensor, C, and the finger tensor, C inverse, and they are in fact inverses of each other, which we could show. The key thing about these is that they contain stretch, but no rotation. So let's take a look at how we might predict. Like, let's go back to that rotating a solid block and see if using these new strain measures have fixed anything. And to do that, we go back to a Hooke's law calculation. Stress is proportional to strain. Only now I put in the new strain measure instead of the old one, gamma. Okay? Now to get this new strain measure, we're good here. It's actually very easy. We have this table. And we have the definition. So let's say the finger tensor is F inverse transpose F inverse. So if we look on the table, we've got F inverse. We can transpose it and then multiply it by itself. Okay? And I don't want to take the time to do that, but maybe you can see that you're going to end up with some things like sine squared plus cosine squared. Okay? If I take, this is F inverse, if I transpose it and multiply it by itself, I end up with, I guess this is showing up funny. I'll take this out of the casing. I can calculate these two strain measures we've been talking about, the Cauchy tensor and the finger tensor, and for this rotation we just get identity. Okay, we just get identity. And that's what we want, right? For this equation says the stress when I do this deformation is going to be the modulus times the finger tensor. And if the finger tensor is identity, it says the stress will be the same when you start and when you stop. Okay? So that works very nicely. That's correct. The stress is the same when you just rotate a block of fluid without deforming it. We can do the same for shear. Okay, going back to this table. We calculated F inverse for shear. We can multiply this tensor by its inverse transpose. Maybe I'll just write it really quickly just so that you'll know I'm not doing anything at all complicated. Maybe I've been talking about complicated things, but it's not at all complicated at this point. It's just going to be take the F inverse, transpose it, and multiply it by itself. So there's F inverse. So it's going to be, the transpose of that is 1 gamma 0, 0, 1, 0, 0, 0, 1, dotted by F itself, 1, 0, 0, gamma 1, 0, 0, 0, 1. Multiply those two together. So you get 1 plus gamma dot squared 0, 0 gamma 0, 0, 0, 1, etc. And that's what we have written here. Here's 1 plus gamma dot, gamma 0, and the rest of the finger tensor. So this is interesting. This is a prediction now. Because this finger tensor goes into this equation, and it predicts that the stress, when you take a block of rubber, something that's an elastic solid, and put it in shear, it's going to generate stresses. And most significantly to us, notice that it's going to predict normal stresses. Okay? So we've got tau equals the modulus times the finger tensor. So we get G times this entry here, 1 plus gamma squared, gamma 0, gamma 1, 0, 0, 0, 1. Okay, so the shear component, tau 2, 1, is just G strain. Stress is proportional to the 2, 1 component of the strain. Perfect. That's what elastic solids do. But look at these ones. Tau 1, 1, tau 2, 2, tau 3, 3. Normal stresses. In shear. This predicts that if you take an elastic solid and just shear it, you're going to feel an upward thrust. Okay? You're shearing it, but you're going to feel an upward thrust. This is some data from Chris McCosco's laboratory in Minnesota, and they checked that Hooke's law prediction. And here's the shear component, that if you shear it forward, you get stresses proportional to strain, correct? And it also predicts that whether you shear it forward or backward, there'll be a first normal stress difference that's positive. It'll push upward whether you go this way or that, and it predicts it just right. Okay? So, although it was a bit theoretical to go into these strain measures and then have to do this polar decomposition, it's resulted in something that we saw no other way to arrive at. It's resulted in an ability to predict normal stresses in shear. Okay? So it's like, in some sense, it's the holy grail. So we've got a new strain measure. In fact, we've got two. We only tried the finger tensor. We've also got the Cauchy tensor. The next step is to take this new strain measure and do what we said we were doing all along, which is fix up the generalized linear viscoelastic model. Okay, so we have, going back, here's our integral Maxwell model. Here's the generalized linear viscoelastic version with the m function in it. It has strain explicit. And so all we need to do is change this strain tensor with the finger tensor. Now actually we're going to do something slightly different. We're going to replace it with the negative of the finger tensor. And the reason for that is because, look at this, t prime. This is t prime t. And so at small strains, negative finger tensor becomes this one. So in order not to change the sign of the equation, we use the negative one. And this gets us a new constitutive model called the Lodge model. This model is named after Arthur Lodge, who passed away last year. He was a professor at the University of Wisconsin, and he was quite an innovator in rheology. So, as always, when we have a new constitutive equation, we have to check it out, see what it predicts, and that's our next step here. And in carrying out predictions of something like the Lodge model, we're going to go back to this table, when we want to make predictions using shear or uniaxial elongation or rotation. We've got these tensors already worked out for us. So you're not going to have to rederive them. They're all sitting right there. Okay, so let's take a quick look at how we would do that. The steady shear material functions for the Lodge model. It goes the same way as it always did before. We have to put in the kinematics and then make the predictions of the stress. So I'm going to predict shear psi 1 and psi 2, which are not both going to be 0 finally, for the Lodge model. Okay, so usually we start with the velocity vector, and in steady shear it's this. We would normally write gamma dot, but we don't actually need gamma dot this time. We actually need the strain tensor, C inverse, which we can get from the table. So C inverse of T prime T is equal to this tensor, 1 plus gamma squared 1 plus gamma squared gamma 0 gamma 1 0 0 0 1. So this is now the kinematics that we care about because of the form of the equation here. After that, it's not complicated, right? We just plug it in. Tau equals minus the integral from minus infinity to t, some constants, the exponential, times this tensor, which has already been written out for us. Okay? So we can do these calculations. I'll point out that on this table, if you forget what gamma was, there's a reminder on the bottom. Gamma is the integral from t prime to t of whatever the sigma dot function is. Let me write that over here. Gamma is equal to the integral from t prime to t of the sigma dot function that we're used to from these calculations. So if we're doing a startup, it would be the integral of the startup sigma dot. In steady flow, it's simpler. It's just this steady gamma naught is equal to sigma dot. So it's equal to t minus t prime times gamma dot naught. Now again, because I'm kind of going quickly, I think you can see what to do from here on. To get the shear component, you multiply up here by gamma, and then carry out the integration to get tau 21. Tau 21 is minus the integral from minus infinity to t of these constants, this exponential, so we just get really to be good at exponential integrations, times gamma, which is t minus t prime gamma dot naught, a constant, dt prime. So you see we have t minus t prime here, we have t minus t prime here. It's an integral over t prime. We can set s equal to t minus t prime. So we get an s here, we get an s here, we get a minus ds here. We switch the limits. We get an integral with a bunch of constants we can bring out to the left. And it becomes an integral of e to the minus s over lambda s ds with some other stuff. Does that make sense? Okay? All of the stuff that's not, that needs to be integrated is in the exponential in this one. This can be integrated by parts, or you can look it up. Carry out the complete calculation. Okay, so it's not too hard. And I'll put the result down. Well, I don't have just the result of that integral. Let's see. But at the end of the day, we then write the viscosity is minus tau 21 over gamma dot naught. And when you carry out all of this calculus, you end up with the final result, which turns out to be incredibly simple. Okay? So in some sense, it's a bit anticlimactic after all of that. What we predict was the same thing that the Newtonian model predicts for steady shear viscosity. But the part that's not anticlimactic are psi 1 and psi 2. So we go back here, and to calculate psi 1 and psi 2, we need tau 11 and tau 22. So psi 1 is equal to minus tau 11 minus tau 22 over gamma dot naught squared. And so we need tau 11 and tau 22. We can't just say they're 0 anymore. So here they are. Tau 11 is going to be this integral with this guy in there. And tau 22 is going to be integral with 1 in there. So tau 11 is minus the integral from minus infinity to t, eta naught or lambda squared, e to the minus t prime over lambda, 1 plus gamma squared dt prime, where gamma is t minus t prime gamma dot naught. So this one turns into e to the minus s over lambda s squared, because this one's going to end up with an s squared in it. And tau 22 is going to be all of the same rigmarole. With a 1 here. So this will turn out to be related to the integral of e to the minus s over lambda. All very doable MathCAD or integration by parts calculations. And the final result for psi 1 equals minus tau 1 minus tau 2 over gamma dot naught squared, and it turns out to be equal to 2 eta naught lambda. Psi 2 equals minus tau 2 minus tau 3 over gamma dot naught. And look at this. Tau 2, tau 3 are both going to be the same. So this model predicts that psi 2 is 0. So the predictions of the Lodge model are summarized on this plot. It predicts a constant steady shear viscosity, and it predicts a constant and larger first normal stress coefficient that is independent of shear rate. So it's a start, but remember that both of these shear thin. Okay, both of these thin. If you go through and do the elongational viscosity, it predicts something very interesting. It predicts a 3 times higher than shear viscosity, which is good. And then it predicts that it diverges to infinity at a critical value of the elongation rate, which is related to this relaxation time. So all along in this course, we've been stepping through trying to get more and more realistic and more and more realistic constitutive equations, but we've kind of been fielding our way along in the dark. We tried making the viscosity just shear thin. We had those generalized Newtonian models. Then we tried to get the time dependence by putting memory in there. And now we've taken a memory equation and fixed up the strain measure, and we finally got first normal stress coefficient. Now, we just picked one of really an infinite number of strain measures, however. We picked the finger tensor. If we picked the Cauchy tensor, things would turn out differently, which I can show you without making any calculations by just looking at the Cauchy tensor. First of all, can you tell me, just from the kind of calculations we've talked about, is psi 1 0 for this model? Shouldn't be, right? Because they're going to be something proportional to this one, and then maybe those ones will cancel, but there'll be something that's non-zero, right? How about psi 2? Is psi 2 0? Not. And in fact, psi 2 is going to be equal to negative psi 1. Can you see that? Yeah. So the Cauchy tensor, just by its structure, tells us that this finger tensor will always predict a 0 psi 2, and it will predict a psi 1. But this Cauchy tensor is going to predict way too big of a psi 2. Okay, we're going to use that fact later, but this is one reason why constitutive equations based on the Cauchy tensor have not been very popular. Cauchy tensor alone have not been popular because they overpredict psi 2. Now, the next step is to fix things up even more. But let me just revisit this example really, really quickly. I'm just going to flash the algebra to you. We talked about the fact that the generalized linear viscoelastic model was wrong because when we did this turntable example, we got that the viscosity depended on the rate of rotation of the turntable, which is nonsense. Okay? And I said that was because the strain measure was wrong. So if that's right, then when I fix the strain measure, this should work. Okay? See what I'm saying? This calculation said that there was something wrong with the math, that when you watched the shear flow on the turntable or off the turntable, you got a ridiculous dependence on the rate of rotation of the turntable. So we can do this calculation, and it's not for the faint of heart. Okay? So let me just show it to you. It's the same calculation, but with the Lodge model. Okay, so the Lodge model, here it is. There's the finger tensor. And when we predict it in regular shear flow, it's just the calculation we did. This is embedded into the calculation for F inverse. And you get the finger tensor. This is the calculation for the finger tensor, which gives this result. And so when you're on the turntable, it's the calculation we just did. When we step off the turntable, we have to relate we have to go back to the velocity here and use a velocity that takes into account the motion of the turntable. That's what we did last time. And like I said, it's not really for the faint of heart. So when I did this algebra myself over a very long period of time, okay, there are lots of sines and cosines everywhere. There's some symmetry that helps you get the algebra correctly, but you can calculate this new vector r that is stepped off of the turntable. That's the hard part. All right, once you do that, you can calculate these tensors, F inverse and F inverse transpose, by taking these derivatives. So for instance, this term is x equals this mess. Okay, and so when I take a derivative of x with respect to x prime, you see there's no x primes, no x. Here's the x prime, so I end up with a bunch of this stuff. And you just have to do all of those derivatives. You get a fairly simple result at the end of that calculation, which is the finger tensor written in the coordinate system off the turntable. So once we have the finger tensor, we put it into the Lodge model, and there's our result. Now, as we did before, to compare it with our previous result, we need to be in a shear coordinate system, which is at time equals 0. So each of these capital S's and capital C's has a time in it, okay? And everywhere there's a strain, there's a time. Okay, so we put time equal to 0, and we get this result. No, excuse me, we get this one. They're the same thing. And so, in fact, we get the same result. There's no, this rotation angle, omega, this rotation of the turntable, it doesn't appear anywhere, and the result checks out. Now, what we're going to do next is talk about some of the arbitrary pieces that we've done to get to this model, because we still want to fix it up. So let's say, what have we accomplished? And I would say the main thing we have accomplished is we found a valid, valid means it doesn't have that problem with the turntable. We found a valid constitutive equation that predicts psi 1 not 0. That's quite an accomplishment. What have we not done is we still haven't predicted exactly how materials behave. What's to be done? We need to predict psi 2. We still need eta varying with shear rate, psi 1 varying with shear rate, etc., and other nonlinear properties. So all of these things need to be predicted. Now, how can we get to these new results? That's the next step. Well, first of all, the finger tensor was arbitrary. So we could try other tensors. And I already talked about that. The Cauchy tensor is 1. We can mix Cauchy and finger. That's just us trying another strain measure. Another way that people fix is, let's say, the form of the equation was arbitrary as well. What I mean by that is the form of the equation matched the Maxwell model. So we could try other forms. And the third thing we could do is something that won't seem as obvious to you. We could try other types of time derivative. And this is confusing. What does this mean? What does she mean? And that'll take me a little something to explain. Try other types of time derivative. So what I mean by that is the Maxwell model we started out with was tau plus lambda d tau dt equals minus eta naught gamma dot. And that became tau equals minus the integral from minus infinity to t of eta over lambda e to the minus t prime over lambda gamma dot t prime dt prime. These are both the Maxwell model. One is integral, and one is differential. This model we can fix up and make a Lodge type model. Tau equals minus the integral from minus infinity to t of eta naught over lambda. Well, I better not. I better put it in as before. M of t minus t prime finger dt prime, okay, where I put in the right m for the Maxwell model. We can take this equation and differentiate it and make a differential version. And that's a calculation I'm going to skip because it takes a little while. So here is the Lodge model, okay, which is the one I failed to write right here, okay. If I differentiate this Lodge model, to find out what the time derivative is and do a little bit of calculation, I get an equation that looks like this. This looks a little bit like the Maxwell model here. Tau plus lambda times a term equals minus eta naught gamma dot. And if we define this term as a time derivative, and here's what it's defined as, then it looks just like a Maxwell model. This model is called the Upperconvected Maxwell model. Very famous. It's in most simulators, Upperconvected Maxwell model. And what it is the differential version of the Lodge model. So maybe I shouldn't have squeezed that last little bit in today. I'll start with this tomorrow, 10 o'clock, and I'm going to talk about this model a little bit and this process of fixing up constitutive equations. And then tomorrow I'm going to move on to talking about fixing up the models in a variety of ways. And what you're going to see is that we've arrived at the point where we can fix them up in more ways than we have energy to try them out. So we're going to have to leave that to ourselves later and go to the literature where people have tried out various attempts at nonlinear constitutive equations, and some work for some conditions, some work for others. And I'll talk about that tomorrow. And then on Friday, we'll talk about molecular modeling approaches that can lead to some of these same constitutive equations. In fact, we're going to be able to arrive at the Maxwell model from a molecular approach just as well as we have arrived at it here. Okay. And then next week we'll talk about rheometry, measuring properties in flows. Okay, so I'll see you tomorrow, or if you can't make it tomorrow, look at it online.